Hi and welcome to this presentation. My name is Ulrika Johansson and I'm a project manager for Visual Sweden. Visual Sweden is to be Europe's most attractive innovation environment for visualization and image analysis. The cluster has more than 100 companies and organizations and connects the industry, research and companies and organizations with needs. During 6 years, we have arranged more than 100 events and 90 projects with focus on society, industry and medicine. Visual Sweden is operated by Linköping University with funding from Vinnova, Norrköping and Linköping Municipalities and the Region of Östergötland. Visual Sweden was a Vinväxt winner in 2016. And Vinväxt promotes sustainable regional growth by developing innovation environments. The goal is to establish Visual Sweden as a national and international actor. We have an impressive innovation momentum in visualization, computer vision, and image analysis in the region. This includes a high percentage of engaged companies. Thanks to the University of Linköping, we can connect several very strong scientific environments to innovation processes in business and the public sector. We are a part of the ecosystem for innovation and growth and collaborate with other initiatives in Sweden and also abroad. Our offer is to strengthen, stimulate and collaborate. And we work with digital maturity, lowering the threshold to use digital transformation technologies, and developing cutting-edge research. In Visual Sweden, we have a very high density of the companies working with visualization, from startups to large companies. And you will meet some of them during this presentation. You can follow us on LinkedIn with this QR code. And Visual Sweden work with verification projects, development projects and platform projects. And you can find more on our website. Please contact us if you have any questions. Today, our focus is on the platform project, Smart Twins for Forest Environments. And you will first meet Martin and Lena, the project managers, and then 4 of our project partners, Atle AI, the Computer Vision Lab, Deep Forestry and Maxar.
Hello, hi, I'm Lena Klasén and I'm the research director at the Swedish National Police Authority, and I also have a position as professor at Linköping University. And I work with the sensors, computer vision, and I am an active part in the project Smart Twin and of course in Visual Sweden too. I'm going to talk about innovation system and how you can actually achieve innovation, or rather how we did to achieve innovations. We started a project called Smart Twin, but I'm going to talk some about the project that we had before Smart Twin, and that is a project we called n-dimensional imaging. Normally you do 3D model of areas, but we decided to include a lot other information as well to add dimension. That is the word multidimensional or n-dim project. And how do we do that? We gather a bunch of researchers and companies and just put everybody together. And we went to the city of Växjö with our sensors and with our algorithms and with our IDs. This isn't an ordinary project. This is a sort of platform when you combine competences, technologies, methods and get common data. And a setup like that, when everybody joins with their own sensor and the methods and the knowledge, is unique, because then you create a lab that doesn't exist in any other form. So we did a lot of measurement and we put all the data together, and the data is actually super good. You can monitor a large area. Maxar, the company, contributed with satellite images and a 3D model of the entire area, Västervik and surrounding. And a company like Mainbase, they had this huge autonomous vehicle that flies with a long wave infrared camera. We had the sensor for underground, underwater, hyperspectral, etc., etc. And then we combined all the data. And when you combine it, you really can have a model that provides you with a lot of additional information that you do not get from an ordinary 3D sensor. As I work for the Swedish police, I am of course interested in crime scene, and National Forensic Center joined in, and they made a high resolution model of a staged murder. And I will emphasize that all what you see in the pictures here are not dead bodies. They are either actors or dummy, a doll. So we did some tests on how to model the forest, how model the airport tower, how model the city, etc., etc. And then we put everything together. So you can go from having a large scale 3D model of the area, and then in that model you can put your high resolution data, you can put infrared data, you can even melt away the ground and look underground, even if we didn't find any buried dog underground. So we just did illustration of how that can be done. But after this project, we had some bilateral cooperation from many of the partners in that, and you will hear more about that from the partner presentations. And we thought that now that we have come together with all the knowledge and all the sensor in the platform project, we were ready to go further to look into smart twin. And really, what is a smart twin? A smart twin here, we use it to denote that is a 3D model, but then you add a lot more information, so like the thermal information, you can add underground, as I mentioned, etc. And that provides you not only a 3D model of a scene, but you can also replay any action that has been taken, like a terrorist attack, or if there is anything else you want to document an analysis. So then we went to the next project, which actually we took all this knowledge and took all the ideas that we had and applied them into forest. And that is the Smart Twin for Forest Environments project.
My name is Martin Holmberg. I work at RISE in Linköping, and I'm one of the project leaders for the project Smart Twins for Forest Environment. Our goal for the project was to create a smart twin process for rural areas, where we can see how we can use digital twins in order to improve many parts of rural life. And we were supposed to use data from many different types of sensors, from satellite sensors, mounted sensors, and sensors put on drones. And then we will demonstrate a smart twin for forestry and for forest fire prevention. And the effect goals of the project is to develop tools and methods for companies to better reach the market, to create new ideas for new products and new services, and also to provide relevant research questions for future projects. The project has run for about 2 years, and it finished by the end of 2022. In the project, we've had a large number of partners. We've had representatives for end users from Mellanskog, Vattenfall, Boxholms Skogar, Skogstekniska klustret, and Räddningstjänsten i Östergötland, the rescue services. We've also had one partner for international collaboration, which was Business Sweden, and a number of partners doing the technical work in the project, which was RISE, the Swedish Police Authority, Linköping University, Royal Institute of Technology in Stockholm, Lena, Deep Forestry, Mainbase, Presendia, Spotscale, Termisk Systemteknik, and Maxar. We've also collaborated with other projects and initiatives like Vaspvara, AgTech 2030, Chalmers Digital Twin City Center, AI Sweden, IoT World, and Atle Drone Services. So why do you want a digital twin, and what can we do with it? Well, there are a number of possible applications. We haven't worked with all of them in the project, but just to name a few, we can look at environmental issues, like how is the environment changing over time. We can look at long-term change detection when it comes to climate changes, for instance. We can use digital twins to study how land is used in different areas, to classify it. We can look at different species to understand the composition of the rural areas. We can look at property and how to evaluate different properties depending on how much forest there is. We can look at power lines and see if we can find trees which are at risk of falling on the power lines. We can look at fire risk assessment, if there are a lot of dry trees or bushes around an area. We can also look at early fire detection to see if there is some fire starting, to discover it very early. We can also use it during a fire to see if we can fight the fire more intelligently. And after a fire we can use digital twins for fire damage reporting and a lot more things. So how do we do that? Well, if you look at the physical world and do a lot of measurements on that, we will gather a lot of data that we can put in a database. And then we can study the data, we can look at information from different sensors, we can fuse data from different sensors and get the information that we are looking for. So that's what you can see on the left side of this image. On the other hand, we can use the same data to create a digital twin, and in the digital twin we try to create a model of the real world that as closely as possible resembles the real world, and there we can give this model some real physical features, and we can use these features to also to simulate the future, to see what would happen if something is changed, what happens if a fire starts here, what happens if we take away trees there. And in that way we can better understand how the forest or the rural area will change over time. And over time, of course, we can gather new data and we can update the model based on this new data. And in the end, hopefully we can get a better understanding and a better model of this area, giving us the possibility to better monitor the environment, monitor forests, or whatever is of interest for us. So in this project, what have we done that hasn't been done before? Well, basically there is a lot of digital information about forests, about rural areas already, but that is usually not in a very high resolution. With the sensors that we are using, we can get a very high resolution with a lot of measurement points in each tree, and that information can be used for a number of different purposes. Also, what we have done is to create the possibility to make quite detailed simulations, because with the data that is available at the moment, we can still make prediction for the future, but not very detailed and only for a few parameters. And in the project, of course, we didn't get all the way to solve all the issues, but at least we have come so far that we have got the high resolution. We have included a lot of new sensor types in the data set. And also we have made it possible to include real-time data in the simulations and in the study of the data. And also, to some extent, we have created methods for automated fusion of the data. In the beginning of the project, we asked our end users, what can we do with this data? Why do we want to do these measurements? And we got a number of answers, and we tried to follow up on these during the project. And one of the first points was the possibility to meet in a digital forest. And why do we want to do that? Well, usually if you have a small plot of land where you have a forest, maybe you often go there, you own a forest, you often go there to pick mushrooms or just to do some recreation. Then if you take away a lot of trees, it will not be very nice to be there. And by meeting in the forest, in the real forest, you can discuss which trees should be taken away in order to still have a nice forest. But sometimes it's difficult to actually go out in the forest, but being able to recreate this environment in the digital world and instead meet in the digital world, then you can do the same type of planning of the forestry together with the forest owners. So that means that we can get a higher value for recreational use of the forest also. Another possibility is to look at individual trees and very early discover if some of them are stressed in some way. Maybe it's not possible to say why the tree is stressed. It might be due to too much water, too little water, or maybe due to bugs or something else, but at least we can discover it quite early. Another possibility would be to plan how to do the logging in the forest in a proper way, and also where to drive the trucks in the forest in order to take away all the logs. And if that can be planned beforehand in a proper way without spending too much time in the forest, we can create less damage to the ground in the forest. And of course, with high resolution, we can do simulations with high resolution, giving us better predictions for the future. Another possibility, which we haven't explored yet, but which could be possible, is to find, for instance, ancient remains that have to be preserved in the forest. Or we can find tracks which animals use so that we don't take away the tracks for the animals and change their habitat too much. What would a digital forest look like? Well, this is an example with images created by one of the companies in the project, SpotScale, where they have used drones to collect data with cameras from a scene in the forest. And as you can see, you can get a very detailed resolution, and you can see the actual images in the end if you zoom in enough. And this way of looking at the environment is very good if you want to have a discussion with forest owners or with other interest groups to see what happens if we take away some trees, what happens if we put a road here, and so on and so forth. So the meeting of people in a digital forest could actually improve the way that we have recreation and the way that we use the forest for forestry and other. In this project, we have seen that there are many possibilities, a lot of things which can be done, and we have quite high commercial potential for many of these applications. And we are now going to ask our partners, what have they seen in this project? What have they done? What have they learned? And what will they do in the future?
My name is Leif Haglen. I'm coming from Maxar in Sweden, and we are a proud member of the Smart Twin project, which is perfectly aligned with our ambitions to build a global living skin of the globe. Maxar operates the best Earth observation satellites, commercial ones I should say, with a collection capacity of more than 3.8 million square kilometers per day. So currently Maxar has 4 satellites in orbit. They have a resolution of 30 to 50 centimeter, and in 2023 we will launch another 6 satellites with a resolution of 30 centimeter. So they will considerably enhance the capacity of the collection during 2023. In Linköping and in the project, we are producing a 3D world, as you see in the center of the presentation here, the image. That's textured 3D skin of the globe, based on satellite images, so it's global. Currently we have built 65 million square kilometers of the globe, and land mass is about 135 million square kilometers. So half of the globe is covered. Based on that 3D surface model, we can generate the digital surface model, which is a pixel-based model with a height in each pixel. We can also, by utilizing deep learning, we can make a land use land cover, and from that we can estimate building vectors, vegetation vectors, which we will look at a little bit later here in the forest environment. And the deep learning is based on an ensemble network, so it's state-of-the-art, where we are also utilizing the DSM, which is unique for us, that we have an elevation model. We also have the NDVI, the Normalized Differential Vegetation Index, which is very important to distinguish buildings from vegetation. We can see roads in purple, ground level in yellow. We have vegetation in green, buildings in red, etc. And this is a fully automated process based on the 3D model. So, for example, here we can estimate the road network in Lebanon, which is not really what you find in OpenStreetMap. So it's a very powerful tool to get really vector data that you can start a reasoning around. We can also estimate the building as vectors, as you can see here, and you can start to see some forest as well. There are individual trees which we have detected. Another example where you can see that we have also distinguished evergreens from the deciduous. So we can have different tree models for the pine in this case, and whatever it is, model of a leafy tree. All of it is also automated. Based on that, we have started to estimate the volume or timber volume in forests. This is a R&D project today, so we are not ready to launch it as a product, but we have started to look at that. And in the project Smart Twin, we have placed a Gysinge as a test area, and here we have a movie of that area. We can zoom in from outer space, and in this case we have just focused on the Gysinge area. So here you can see the land use, land cover. Green is vegetation, and you have roads and ground. Not that many buildings in this area, but you can clearly see how the structure of the forest. You can see that there are different species as well, and this is what we can do. In this case, we have collected all the satellite images that this is based on in June 2022, specifically for the project. So this is a unique collection which we can use together with all the other sources in the Smart Twin project to get a sort of a data stack with different modalities. So here we have some images of the same area. You can see the land use, land cover, roads, ground, different types of ground. Yellow and brown is two different types of ground. And then another example. And at the end here we have the estimated trees. So here we have placed tree models where we think there are trees, and we have estimated that. And with a very preliminary R&D test from last week, it was close to 1 million trees in that area. Might be 2 or 3 more, but we're not totally sure there. Now, so that's Maxar's contribution in the Smart Wind project, where just the data collection and the collection of all the data we have from different modalities will turn out to be a possibility to reasoning around a smart twin and a living one, where we hope to generalize this to global scale in a pretty short future. Thank you.
Hello, my name is Per-Erik Forsén, and I'm a professor at the Computer Vision Lab in Linköping, and I'm a partner in this Smart Twins for Forest Environment project. So I'm here to talk about the Smart Twins for Forest Environment project, and specifically about how we make use of robust 3D modeling and point set registration. And in the Smart Twin project, we make use of a large variety of imaging sensors. We have satellite images collected by our partner company Maxar that collect images from space, and then from these we can then compute 3D models using triangulation. We also have color cameras and infrared cameras mounted on drones, and we also have a partner company, Lena Sensors, that have developed an hyperspectral camera, and that one is also used. And I'm mainly going to talk about LiDAR sensors. So we have LiDAR sensors that are mounted on drones, and we also use LiDAR sensors that are mounted on a stick, and we then walk with a stick to access more difficult areas in the forest. So the purpose of this is to collect different types of modalities and to fuse these into a coherent representation of the forest, and that can then be used for analysis. So the key to build a 3D model from images is to use a technique called structure from motion. And structure from motion makes use of a camera that is moving over time. And by simultaneously estimating the motion of the camera and then triangulating the scene points, we can compute a dense 3D model from video or still images. And this is done, for instance, in this illustration by the company SpotScale. So here we have a large patch of forest that has been triangulated, and the camera motion has been estimated. So this model has been developed mainly by SpotScale, but it's also a collaboration with RISE, who has collected the imagery, and by the computer vision lab where the cameras have been calibrated. So 3D models from LiDAR sensors are done in quite a different way, because here we have direct measurements of 3D. So a LiDAR sensor emits light and then counts the time until the light reaches the sensor again. And this is the same principle as radar, time of flight sensing. And essentially you count the time and multiply by the speed of light and divide that by 2 to get the distance. And we make use of small compact automotive LiDARs from the company Auster in the Smart Twin project. And here we see an example of this. So these sensors are small and sturdy, and they have inertial sensors in them that can be used to sense the motion of the sensor and also to compensate for the motion, to avoid motion distortions. So here we see an example of the data that comes out of an automotive LiDAR. So in this case we have mounted the LiDAR on a stick and walked with it, as can be seen in the illustration to the left. So to the right we see a point cloud at the bottom, and at the top we see the reflectance data and the depth data from the sensor. And as we can see, it's a lot of data. So 10 times per second we get one of these point clouds. And in this illustration we see what happens when we fuse these into one coherent model. So here we have stitched thousands of point clouds into one single geometrically coherent model by aligning the point clouds and putting them in the same reference frame. And as can be seen, this becomes a quite detailed model, and then after we have all these points in the same reference frame, the next step is to somehow simplify and analyze the data. So due to the very large amount of data, we need to have automatic detection of failures, and that's something we've been working quite hard at improving. So in our alignment algorithms, we use 4x4 groups of point clouds, so we register them 4x4 together simultaneously, and we automatically detect if one of these point clouds are not as well aligned with the others, and then that one can be either discarded or the initialization can be modified to it and the alignment restarted. So here we see an illustration of alignment of 4 point clouds. So we have 4 point clouds in the corner, and in the center we have them put in the same reference frame. And so in order to do this, we need to estimate 4 transformations that go from each individual point cloud to the common joint representation. To do this in parallel makes the estimation more accurate and reduces drift in the final model. And we make use of an algorithm called Joint Registration of Multiple Point Sets, or JRMPS, and that algorithm has common representation in the common reference frame that is based on a mixture of Gaussians, and then each point set is registered with respect to this common point set. And we have extended this basic model with deep learning to also learn a description of local appearance in each point cloud, and that improves the robustness of the registration greatly. And we also learn an interest operator that weighs different parts of the point set differently. So more informative parts of a point cloud are weighted higher, and these methods are documented in a conference paper in the International Conference on 3D Vision and in a LiU master thesis.
My name is Magnus Blomberg, and I'm from Atle, and at Atle we changed the way that drones are used in the forest industry. So today you typically have a forestry expert that is in the field, flying a drone, looking at the controller and trying to identify damaged trees or windfrows or other areas of interest. So what we do is we separate the data collection from reviewing the results. So we have a process that enables us to collect data and then ensure the quality of the data. And after that we process this data. We create different kinds of artifacts. We create a georeferenced orthographic photography that you can overlay on a map. You can zoom in and out as you are used to. We create 3D point clouds and other artifacts. And these artifacts are then used as a basis for different kinds of AI analysis. So the forestry expert can then be in the office reviewing these results and have an easier way to plan different actions based on these results. And if something needs to be checked in the field, then at least it is possible to select different areas of interest to investigate further. So in the Smart Twins project, we arrived quite late after having presented our way of visualizing these kinds of data. So we have a simple and quick way of importing georeferenced information and visualizing it. So you can import different kinds of layers and toggling their visibility and have a simple way of looking at this data on top of each other. So this way of separating the data collection from reviewing the results and presenting refined information to the forestry expert greatly leverage the use of the expertise. And the simplified process of getting this information to the forestry expert also saves time. Values in the forest can also be identified and handled, values which otherwise would have been missed. And all in all, this is a very cost-effective and time-saving way of getting the information that is needed to the forestry expert, allowing the expert to make decisions on future actions.
G'day, Levi here, CEO of Deep Forestry. What we do is autonomous drones and also 3D machine learning algorithms to look into forests for biodiversity, carbon flux, things like that. So we were very blessed to be a part of the Smart Twin project. And during the project, our core technology increased from a TRL level of around 6 to 8 for a variety of factors, and some of those were from the great work that was happening within the project. We surveyed a variety of forests for Swedish customers and gained insights to the customer needs during the project. And we also managed to present data acquired from the Smart Twin project both locally throughout Sweden and Europe and also on the global stage, and that helped us gather traction with customers and investors. Another result of the project, and maybe perhaps the best of all, is that by leveraging some of the data and the good marketing and the customers that we met and the insights we gained during the project, we actually managed to hook a few investors, and that helped us secure actually a 9.5 million crown investment round, which we closed soon after the project completed. So that was a great result of the project. Another thing that helped us was the network of the Smart Twins project. So this created a great foundation for our company and a launch pad into different opportunities. One of the most valuable results was that one of the Linköping University's master's students that was working in the project for a different stakeholder, we actually met him out on the site, and now he became an employee of Deep Forestry. And he's now our head of simultaneous localization and mapping. And he's rolling out a new above and below canopy mapping systems for deep forestry that our customers will be using this spring. So that was a huge benefit of the project to actually meet him and get him on board. We actually also, from that network, gained research and development connections with Linköping University, RISE, Visual Sweden, as well as other partners, for example, Maxar and others that we have had new follow-up projects with, and there are a lot of exciting areas of development associated with Smart Twins, but also associated with new opportunities using this network to kind of foster and develop those. And we also managed to get funding from government agencies, EU, Sweden, from these networks. So huge value added there from the networks. So Deep Forestry is a vastly different company as a result of some of the things that happened in the Smart Twins project. When we started, we actually just had a prototype, so we didn't really have any product that we could sell. And we were just looking at kind of local companies for support. But by the end of the project, I could safely say Deep Forestry has become a world leader and a global player for the production of digital twins, smart twins, and autonomous robotics. And you can see that with the customers that we've secured. I mean, we just got back from Tokyo recently, flying our full systems and developing smart twins for Kojima Corporation, one of Japan's largest construction companies, for example. But then we've got projects like this all over the world at the moment. So a lot of very interesting insights came from this project. So the next thing I want to do is walk you through the data that we acquired during the project and give you guys a sneak peek at our guided user interface for deep forestry and how we use Smart Twins in the cloud as a visualization tool that we're selling to our customers. Okay, so here is the login portal. And if we look at Smart Twin data, you can see where it is in the world. So anytime our drones fly, they pop up onto this map. Zooming in here on some data that we surveyed during the project, you can see the shape files of where the drone's been. And then we move to have a look at the individual trees on that site. So we have a whole bunch of different types of information here, the diameter, wood volume, and a summary of the forest site itself, along with adjacent files. You can see in the histogram every individual tree has its exact location and all of its individual understanding. So this is our smart information on each individual tree. And then you can see here in the 3D viewer, all the individual tree numbers are there. So we'll just remove those because you can't see the point cloud. And then we will slowly fly into this site and have a look around at what our Smart Twin looks like. So this is a site that we surveyed during the project. You can see here the parking area where we started, and the data is slowly uploading. It takes a little bit of time before the data uploads. And you can kind of see our machine learning algorithm has segmented each individual tree. The tree trunks here are in orange, the terrain in green, and the leafy parts of the trees in purple. As well, you can see we've identified a tree on the ground there as well in a lighter green color. So these are just the basics of our Smart Twin. You can see that there's more information here than just a digital twin. with every individual tree carrying information about that individual object. And in future this will be different objects, you know, like if we find some important mushrooms or biodiversity things such as this tree on the ground here, all of this information can be incorporated into this portal and used by our users. So there's a good demonstration of our Smart Twin.
So when we have finished the Smart Twin project, we realized that there is so much more we can do. So there has been a number of spin-off projects from the Smart Twin. We have, for example, there was actually one company established in the Smart Twin project that look at sort of outdoor fire alert systems. And I'm going to talk more about another spin-off project. And as I said, I'm within forensics and within law enforcement, and we are of course extremely interested in crime scenes. So we have a project now together with gaming industry, Sweden Game here in Linköping, and a company within their organization. So we actually staged a murder, and again I would say that this is what you're going to see. It's not real murder. But stage murder. There are two actors, and here the problem is to figure out who did what. And in this case, you see person coming in, and some when they go through a surveillance camera, but when they're out of the field of view of the camera, there is a murder, and then they enter the second surveillance camera, and there is also a public recording by an iPhone of people nearby. And here the task is to actually figure out what happened. And here we combine the knowledge that we have from the ND project and the Smart Twin project, use data from National Forensic Center that did the 3D model of the city view, and we took the surveillance video, and then you can actually reconstruct the event with the persons in it. And that is to take it a bit further. So before we worked with static scene and static objects, but now we also can include human action in that, as you can see in the example of the video. And this, beside another effort that we have to go on working with Smart Twin of city areas, is a little bit what you have seen here today. So thank you.